subscribe now and press the bell icon. Never miss an update.
Good morning, students. Now you have seen yesterday that when a beam of light, whether it is convergent, divergent or parallel beam, falls in a lens, two things happen. Either the incident beam is further converged in the case of converging lenses or convex lenses. The incident beam in the case of concave lens diverges. So that is the basic function of a lens. Lens therefore is an optical medium which either converges or diverges the incident beam of light. Now, if we have a system of more than one lenses, as in the case of cameras, now let us see how the combination works. Now therefore, we will now be discussing the lens combination formula. This is another favorite question for the board. Now, I'll consider two thin lenses. Thin lenses means the thickness of the lens is very small compared to its focal length. L1, L2, placed coaxially. Let us suppose O is a point object. Consider two thin lenses L1 and L2 of focal lengths F1 and F2 respectively, placed coaxially. That means the axis of L1 coincides with the axis of L2. O is a point object. On their common axis. Let us consider light going from O. A ray of light traveling along the axis falls here normally, so continues to travel in the same direction, again falls normally, like this, it goes in the same direction. Any other ray like this. Now remember, you have light here, light beam. Now this undergoing refraction would have formed, see, on account of refraction in the first lens, an image here. If this is not there, if only L1 had been there, the light from O undergoes refraction here, forms an image at dash. But before that happens, now the light coming out of the first lens, see, again refracts, forming the final image at I. Now we'll consider each lens separately and write out the lens formula for them and see what happens. Say light from O falling on L1 would have formed image at I dash. But light coming out of L1 again undergoes refraction and forms final image at I. See, this light would have gone like this and formed the image, but it again undergoes. See, there is refraction here, there is refraction here, two refractions taking place like that. Now, so you will consider the first lens. See, for refraction in the first lens, we have from this equation where, see, this is the image distance, distance of I dash from the lens system, U is distance of the object from the lens system. Now, I dash, that is the image formed in the lens L1, acts as virtual object for refraction L2. Therefore, again from one over f equals 1 over v minus 1 over u, I apply this relation. See here, the focal length, the second lens is 1 over f2, image distance, now this is the image distance, so 1 over v minus, now here this is the object distance, 1 over v dash, equation 2, where v dash is image distance with respect to L2. V dash is the object distance with respect to L2. Now adding equation 1 and 2. Equations 1 and 2, we get this is added on to this. See 1 over f1 on the left side of the equation 1, 1 over f2 on the left side of the equation 2, that is equal to 1 over v dash minus 1 over u of the first equation, added to that 1 over v minus 1 over v dash. this cancels, giving you 1 over f1 plus 1 over f2 is 1 over v minus 1 over u. I will call this equation 3. Now, observe, what are these lenses doing together? What are these lenses doing together? See, light coming from O, after refraction both the lenses would form here an image. Now, I keep, let's suppose, a single lens which does the same function, Now, if say f is the focal length of an equivalent lens that is the lens which produces the image of the object O at the same position. Then we have 1 over f equals 1 over v minus 1 over u. We will call this equation 4. Compare equation 3 and 4. Comparing equations 3 and 4, we have see 1 over f is equal to 1 over f1 plus 1 over f2. This is the equivalent lens formula. In fact, this can be generalized for any number of lenses, maybe convex, concave, or concave, convex, whatever it be. In general, 1 over f, 1 over f1 plus 1 over f2 plus 1 over f3, etc. Now, remembering that the reciprocal of the focal length is the power of the lens, that is the ability to converge or diverge the incident light. We have 1 over, P is equal to P1 plus P2 plus P3, etc. So, this is also over there. Now, we shall move on to another important concept. See, we have seen refraction through a plane surface. See, whenever light passes through a plane surface from one medium to another medium, there is change of direction. This we call refraction. And we have seen refraction through a glass slab like this, light passing through this surface, comes out through the other surface, opposite face, in the same direction. So, there will be a shift in the direction, in the path, not change in the direction. Now, instead, see, if the opposite faces, if they are not parallel, if they are like this, let's suppose, if they are, this is a plane, this is a plane like this. Now, in between these two planes, let's suppose, you have a plane like this, you have a plane like this. Now, these are two parallel planes. Now, if you have a plane like this, let's suppose, and if you have in between these two plane surfaces, it is only these two plane surfaces, not this surface, not this surface, that is important. Then we call the medium to be a prism. So, prism we are considering now, refraction through a prism. Now, is any transparent medium bounded by two plane surfaces? Please note, I am speaking only of two surfaces, this and this. I am not interested in this, or in this. So, that is what we are discussing now. Say refraction through a prism. So, a prism is any transparent medium bounded by two planes called refracting planes. Now, with reference to this figure, this is one plane, this is another plane. See here, the refracting planes A, B, C, D, and then E, F. See, these are refracting planes A, B, C, D, and A, B, E, F. See, these two planes A, B, C, D, A, B, E, F, make an angle between them. The angle between the refracting planes is called angle of the prism. Now, here it may be CAD, not CAD, FAD, and EBC, like that. See, the two planes. See, here you have a plane, here you have a plane, here you have an edge there. That is called the refracting edge. The line along which the planes meet is called refracting edge. Refracting edge. Now, let us suppose I have a plane like this, which is perpendicular to the refracting edge, Now, this is called the principal section. Any plane of the prism perpendicular to the refracting edge. Now, these are the terms that we come across. To repeat, you have the prism, transparent medium bounded by two plane surfaces like that, and the angle between the two planes, angle of the prism, the line along which it meets, refracting edge, and a section of the prism, that is plane perpendicular to the edge, is called principal section. See, when light goes here, let's suppose like this. Now it changes the direction. Now here, this is the normal. It deviates towards the normal. Now remember that the normal, the incident ray, the refracted ray are all in the same plane. Again comes out like this. Now deviates away. So these are also in the same plane. Now remembering that the incident ray, the refracted ray, the emergent ray all lie in the same plane, I need not have to write the prism, this figure always. I will concentrate only on the principal section. Now, consider principal section ABC of a prism. In the figure, ABC is the principal section of a prism of angle A and of material of refractive index N, placed in, for convenience, air or any other medium for that matter. PQRS, PQRS is the path of a ray of light through the prism such that PQ is the incident ray, QR is the refracted ray, and RS the emergent ray. Emergent. Mn and Mn dash. Mn dash are normals as shown in the figure. That is, Mn is the normal to the first surface at the point of incidence Q. N and Mn dash is the normal to the second surface at the point of emergence R. Now we have P, Q, N. Observe the figure. Is I1 the angle of incidence at the first surface, at the first phase, and MQR, R1 the angle of refraction at the first surface, and then QRM is R2 the angle of incidence at the second surface. Please note, light falls here on this surface, therefore it is angle of incidence, goes out here making an angle of refraction. I2 that is S or N dash. S or N dash is I2 is angle of refraction at the second surface. It is more commonly known as angle of emergence. Angle of emergence. See, you see that light passing through the prism deviates here. This is one deviation, please note. Instead of going here like this, again deviates. This is another deviation, please note. Deviates twice. So this is total deviation. Total deviation. Now that is the angle between the incident ray produced and emergent ray produced. See, PQ produced and SR produced. Meet at T. The angle between the two gives the angle of deviation. The angle of deviation, D. So that is what we have in the figure. Observe the figure. We have several triangles, quadrilaterals, etc. From the quadrilateral AQMR. See the angle AQM, the angle QMR, the angle MRA and the angle RAQ. Together make 360 degrees, 4 right angles. But see, AQM angle is a right angle. MRA is also a right angle. Now therefore, substituting, we get QMR, this, plus RAQ. Now together make 2 right angles, because this is one right angle, this is another right angle. Substituting and rearranging, we get this. Now I will call this equation 1, let's suppose. Now let it be. Now again, from, see the triangle QMR, we have QMR angle plus MRQ angle plus RQM angle, also make 180 degrees. So you can equate these two. Now therefore, QMR angle plus RAQ angle is equal to QMR plus MRQ plus RQM. QMR is common. Now RAQ, that is the angle of the prism, that is A. Now RQM angle. RQM angle is R1 plus MRQ is R2. This equation we will call 1. Now before we go further, notice the significance of this. Now once I construct a prism like this, let's suppose, the angle A is fixed. Now R1 and R2, if you enter like this, if you enter at different angles, R1 and R2 change, but together they do not change. That is the significance you have to observe here. Whenever refraction takes place in a prism, the angle of incidence at the first surface, the angle of refraction at the first surface, the angle of incidence at the second surface together remain the same. Now again, from in triangle, see this triangle, this side is produced. So exterior angle is sum of the interior opposite angles. See, in triangle RQT, see, QT is produced. To T. Now therefore, exterior angle, this is a famous theorem, exterior angle is equal to sum of interior opposite angles. That is, exterior angle is UTS. Interior opposite angles, it is RQM plus MRQ. That is angle of deviation, that is the angle between the incident ray and the emergent ray produced, is equal to RQM. Observe the figure, RQM. See, it is I minus R1, I minus R1, I1 minus R1 rather, plus MRQ. Now this is I2, now this is R2, therefore this is I2 minus R2, I2 minus R2. So that's equal to, simplifying, I1 plus I2 minus of R1 plus R2. Since R1 plus R2 is A, we have delta equals I1 plus I2 A. Equation 2. See, look at this equation. Delta equals deviation is I1 plus I2 minus A. Now we find that delta is a function of I because this is fixed. Angle of incidence it is. Now delta depends on I, whether it is I1 or I2. If you enter from this side, I1 is I. If you enter from this side, I2 is I, like that. So it depends on I, the angle of incidence. The angle of incidence. The variation of delta with I is as in the graph. See, this is the graph experimentally, like that. Now, for any deviation, observe you have I1 here, I2 here. For this deviation, I1 here, I2 here. For this deviation, there is only I1 and I2 coincide. So, here when delta is delta minimum, which we denote by capital D, I1, I2, I1, I2 become equal when delta is delta minimum. Say I1 is I2. So, each equal to I, let us suppose. When they are not different, when they are same, we will denote both of them by A. And we can show that R1 and R2 are also equal, like that. Now, substituting in equation 1, this is equation 1. A is R1 plus R2. Now that becomes, that is R is A by 2. Again, from equation 2, that is delta equals I1 plus I2 minus A. When delta is minimum, you have capital D, I plus I minus A. That is 2I is A plus D, or I is A plus D upon 2. So, you have R I. Remember Snell's law. From Snell's law of refraction, which goes like this: sin of I upon sin of R. Substituting here, we have n equals sin I sin of A plus D by 2 upon sin of A by 2. So, this is the expression for the refractive index of the material of a prism in terms of the angle of the prism, which is a constant, the angle of minimum deviation, that is also a constant. Now, if the angle of the prism is very small, let us suppose, or the order of 3 degrees, 4 degrees, like that. Now, remembering the relation A is R1 plus R2. So, R1 plus R2 together will be 3 or 4 degrees. So, if R1 is 1 or 2 degrees, 2 or 3 degrees, like that, I1 also necessarily will be 1 or 2 degrees, 2 or 3 degrees, like that. So, in such a case, we have the small angle prism. So, for a small angle prism, if A is very small, not 0, very small, then R1 and R2 are also small. Hence, I1 and I2 are necessarily small, so that say angle A is small, A plus D will be small. Say if since delta is made of I1 plus I2 minus A, this is small, these are small, therefore See, delta is also small. That is, the angles A and D are also small. Now, therefore, from say n is sine of a plus d by 2 upon sine a by 2. Say when theta is small, say sine theta in the limit can be written as theta. Thus, n is a plus d by 2 upon a by 2. Simplify, n into a by 2 is a by 2 plus d by 2. 2 is common in all of them, you can remove, so that deviation is equal to n of a minus 1. In general, now notice that there is an interesting phenomenon here. The original derivative equation delta is I1 plus I2 minus A. The graph looks like this. It depends on I, but here it doesn't depend on I. So for small angle prism, delta is same for all angles of incidence. Now that is the interesting part of that. Okay, we'll conclude here, continue next time.